Hi everyone, welcome back to Fundamentals of Engineering. Let's solve an interesting problem in axial load and deflection of member. If we have such configuration, which a rigid bar BDE is connected with two rods to the ceiling. One of them is aluminum, the other is a steel, and their specification is provided. We want to know what is the deflection at B, D, and E due to loading of 30 kilonewton. So in our problem, the rigid bar BDE is connected with a steel and another aluminum rod to the ceiling. Their length are provided and their cross-sectional area and also modulus of elasticity of each of them are provided. We want to know what is the deflection at point B, point D, and respectively at point E. Let's approach our problem. So in such problem, first we need the equilibrium equation, and then we do know that we need a extra equation which is a compatibility in our case. So again, if a rigid bar BDE is connected with two rods to the ceiling, one of them is aluminum and the other one is a steel. The aluminum rod is provided with the cross-sectional area of 500 millimeters squared and modulus of elasticity of 70 gigapascal. And for a steel, we have like area is 1600 provided to be 1600 millimeters squared, and E modulus of elasticity for a steel is 200 gigapascal in terms of SI units. So we want to know what is the deflection at B, D, and also E. So first of all, we need to draw the free body diagram for rigid bar BDE. And if you do so, you can easily see we have like FAB and FCD in each pin at B and D. And 30 kilonewton is applied downward in at E based off problem statement. So by jotting down the moment equilibrium against a point B, we can get FCD, but FCD is, and that's a positive 90, which means that's a tensile force. So there is a tension in bar BDE, and by summation of moment about D goes zero, FAB is a negative 60, and negative means that's a compression. So by flip-flop the arrow at FAB, it just gives a correct a free body diagram of what we are drawing here. So if that's the case, so let's jump to point B over here. So if there is a pin over here and there is a compression force like FAB, the same kind of force is applied to the member BA or AB. So if this is a push, it should be also a push to member. So definitely we do know the aluminum is getting smaller in size due to this a compressive force. Vice versa, if FCD is a tensile force, so if this is pin at D and there is a force which pulls the pin upward, so the same reaction applies to the bar. So if this is DC and this is a tensile force, tension applied to the pin at D, so the same kind of force should be applied to the member. So that's a tensile. So we definitely know that DC is increase in size and AB is decrease in size. So that's just the intuition based of free body diagram. So if we jot down the equation for B, which is delta B is equal to PL over EA. And if we just replace our numeric value, a negative 60 kilonewton times the length of that member over modulus of elasticity and cross-sectional area. This is cross-sectional area in meter square, and this is 70 a gigapascal which is provided. You can reach to this numeric value, and negative is just its upward, and delta B is 0.514 millimeters upward as we expected. This is a negative in size, in length, and CD is a positive in length. So it just moves upward. It just says AB shrinks. And if we make a comparison between a member AB, rod AB, which area is provided, modulus of elasticity provided, length is provided, we already get the forces from free body diagram, and that's a compression. And for rod DC, which is made of steel, their modulus of elasticity, cross-sectional area, and force is provided. And this is definitely in tension, and AB is definitely in compression. So for deflection at D this time, we just jump here. We can replace numeric value of a tensile force FCD, which is 90 kilonewton, and the other specification are provided as we reviewed in previous slide, and that's delta D, and that's positive, that's a downward a movement. So that's 0.3 millimeters downward. As soon as we get delta B and D, we were looking for delta at B, delta at D, and delta at E. So far, we get the two of them. Let's jump to see how we can calculate delta at E. So by BB prime, we mean that's delta B. By DD prime, we mean that's delta D. We already know what delta B is. We calculated, and that's an upward movement. And for delta D, we already calculated, and that's a downward movement. So, and definitely we do know this length is 200. If we just call this length like x, and this is definitely 200 minus x, and if we just jot down the equation, then we are looking for deflection of E. So if we just jot down BB prime over DD prime, this over this is equal to BH, this length, over DH or HD. And the only unknown in this equation is x. If you solve it for x, it just gives you x is equal to 73.7 millimeters. So we already know what x is. As soon as we know that, we can write down again equation for EE prime, which is delta E, over DD prime over DD prime is equal to HE over HD, total length over HD. So we are comparing this big triangle with this small one here. So in that case, we already know what EH is. That's 400 plus X, which is just come from here, over HD. So the only unknown in this part is delta E. And if you replace in the equation, it just gives you delta at E is equal to 1.90, almost 1.9 millimeters. And definitely that's a downward motion. So in such problem, you need to uh, solve the equilibrium equation to get the forces, and then just come to the relation of displacement to get the deflection of each pin or member. Thank you. We'll solve more problems.